Hi, I'm Jeff, and I'm a senior analytic trainer at SAS. In this video, I'm going to talk about lift charts in SAS. Now, actually, this video is part 2 in a series of videos that I'm doing on graphical tools to assess model performance. My earlier video was on ROC charts. Take a look down below in the description for a link to that video. And now I'm going to talk about lift charts in SAS. Now, lift charts are a graphical tool to assess models that are built on a binary target. Just like the ROC chart, we can use lift charts to assess the performance of a single model, but probably the way they're used most often in practice is as a model comparison tool. Several models are built, put all of them on a cumulative lift chart, and use that tool to pick the best one. Now, to get to cumulative lift is actually a multi-step process. So along the way, we're going to be talking about a couple of other statistics. Primarily, the one that we'll be talking about is the cumulative response rate. Now, I want to review some terminology first, terminology that was introduced in my earlier video. Just like in that earlier video, we're going to work out a lift chart by hand. Yes, that's right. I said we're going to do a chart by hand because going through the construction manually, seeing how the chart is actually constructed using good old pencil and paper is going to help us interpret and gain more insight out of the plot when we get to the computer. We'll wrap up the video by doing a demonstration. I'll be using Model Studio in SAS Viya, and we'll be taking a look at some real-world data there. All right, without any further ado, let's go ahead and jump into the whiteboard. Now, the basic way that we can assess binary models often starts with a confusion matrix. And again, just refreshing some of the terminology that I introduced in my ROC video, we've got the 2x2 grid confusion matrix shown on the whiteboard. On the left-hand column, I've got the observed outcome for each observation. So historically, whether the outcome was a known event, a 1, or a non-event, a 0. And across the top, we've got the predicted decision for each case. Now, maybe there's a probability being used under the hood, but ultimately what we're doing is assessing the decision prediction, the model deciding whether each case is a 1, an event case, or a 0, a non-event. Now, in the ROC charts, a lot of the discussion was based around true positives, the correct decision in that 2x2 table that appears in the upper left-hand corner. Cumulative response charts are going to be using that true positive rate also, but we're dividing by a different marginal total. In response charts and lift charts, we're interested in the total number of cases that are predicted as 1s. Cumulative lift charts, response charts are widely used in applications such as marketing. In a marketing context, I might be interested in answering the question of all the people that I've contacted. That means of all the people that I've sent a marketing campaign to, what percentage is actually responding? That is the response rate. Now, lift, we'll be talking about that a little bit more as we go on. Lift is actually comparing the response rate of your model that's being investigated compared to the response rate of your naive model. But let's not get too far ahead of ourselves. Now you see a real simple equation for response rate, or more accurately, what we'll be calculating, cumulative response rate. The response rate is the number of true positives divided by the total number of predicted positives. And we're going to do that calculation at different depths or deciles down the rank order of our observed predictions. So here's our very simple example. If you saw my video on ROC charts, the numbers look familiar. It's the same exact scenario. I've got 5 customers. Each customer historically was either an event case, that means the observed target was a 1, or they were a non-event, the observed target was a 0. Now notice that historically, if we look at all the cases, the prior event rate is 3/5. Out of all 5 customers that we have, we know historically 3 of them responded. We'll be needing that value later when we get to cumulative lift. All right, we have the predicted column. Remember that that's where the model's being involved. In this case, I don't even know what the algorithm is, but it's giving me predicted probabilities, and I'm going to use those as the starting place for constructing the cumulative response or cumulative lift chart. So just like with the ROC chart, I'm going to sort by those predicted probabilities. That gives me a list of customers from most important all the way down to least important. Now, you see by each of the sorted probabilities, I have a numeric value in parentheses, a 1 or a 0. And that's just letting me know what the actual observed outcome was for each of those predicted probabilities. For example, we see that the case predicted as 0.9 is the top customer in my sorted list. Well, if we look at that record, the case predicted is 0.9. We know the observed outcome for that case was a 1, and that's why I've got that 1 there in parentheses. That'll help me keep track of which cases were known 1s and which cases were known 0s. All right, that last column to fill in, we're looking at cumulative response rate. I'm abbreviating that CRR, and we're going to do that calculation at certain depths or deciles in the data. Now, in real-world applications, the charts are usually constructed using demi-deciles or 5% chunks, top 5%, top 10%, top 15%, and so forth. But with only 5 observations, we're limited on how many deciles we've got. We're going to be looking at things in 20% deciles along the way. All right, let's do some calculations. So we'll take a look at the top 20% of cases in our sorted list. Well, everybody that's been captured, we're labeling as a 1. That's like in a marketing situation, how many people am I sending my marketing ad out to? Of everybody captured, how many actually were 1s? Well, we captured one person, we're labeling them as a 1. Historically, we know their observed outcome was a 1, so my cumulative response rate up to that decile is 1 out of 1. I've correctly captured one case that was a known 1 out of 1 captured. The cumulative response rate is identically 1 at a depth of 20%. Let's go a little bit deeper down our list. So now I go to my next decile, 40% or 0.4. Similar calculation. Everybody above that line I'm labeling as a 1. Those are all people that I send my marketing ad to. But of all the people that I'm contacting, how many historically actually were known responders? Well, I've captured 2 individuals at that decile. Both of them were known to be 1s historically, so my cumulative response rate is 2 out of 2, or in other words, it's still equal to 1. No change in cumulative response rate yet. Let's go further down the list. All right, now I'm looking at the top 60% of all of my cases, or a decile of 0.6. I've now captured 3 cases in total. I've marketed to all 3 of them. How many were actually known to be responders? Well, now my cumulative response rate drops below 1. My cumulative response rate at that decile is 2/3. Out of the 3 individuals captured, 2 of them were known to be observed 1s. Let's go a little bit quicker now. Further down my sorted list, I'm at a decile of 0.8. I've captured 4 individuals now, but of those 4, 3 were observed to be event cases. My cumulative response rate to a decile of 0.8 is 3 out of 4. And by the time I'm at a decile of 100%, or I'm looking at the entire list, well, the cumulative response rate has to be the response rate that I started with historically in the data set. I've captured everybody here, so I've captured 5 cases. 3 of them I already know to be true 1s, so my cumulative response rate is 3/5. Now, going from these values to cumulative lift is quite easy. I'm simply taking all of them and dividing by a constant. Each of those cumulative response rates I divide by 3/5, which is the prior event rate that we have historically in the data set. Let me first start by plotting the cumulative response values on a table. All right, I've got cumulative response rate plotted vertically, ranging from 0 to 1, and I've got my decile across the horizontal axis. Let's go ahead and start plotting some points here. At a decile of 0.2, I know the cumulative response rate was 1. So my first plotted point on the chart right there. At decile of 0.4, the cumulative response rate did not change. It still is 1. There's my second point there. At a decile of 0.6, my cumulative response rate dropped to 2/3, somewhere probably around that neighborhood. At a decile of 0.8, my cumulative response rate ticked up a little bit to 3/4. And then when I'm at a decile of 1, or I'm looking at the entire list, my cumulative response rate has dropped down to 3/5, somewhere right around there. So my cumulative response chart would start at 1, and it would tend to decrease as we get deeper down the list of sorted cases. But we do see that starting from 1, we have to get down to the prior response rate when we look at a decile of 1. Now, cumulative response rates can be informative to look at, but lift is probably a little bit more interpretable, again, because it's a comparison with where we're at to the naive model. So I'm dividing all of those values by the constant 3/5. That means the actual line itself is not going to change, just the vertical axis, the scale on the vertical axis. So cumulative response rate will become cumulative lift. The response values that were 1, I'm dividing those by 3/5. 1 over 3/5 gives me a cumulative lift of 5/3. So on the cumulative lift scale, that's the higher value there for those more shallow deciles. And I like that that cumulative lift value is above 1. That means that the model I'm investigating is doing better at capturing responders compared to just the naive model. And of course, that last value at a decile of 1, we know the cumulative response rate is 3/5. If we take 3/5 and divide it by 3/5, the cumulative lift ends up being 1. So again, only that vertical axis changes when we go from cumulative response rate to cumulative lift. Lift gives us a direct comparison of our model that we're looking at compared to the naive model. All right, let's go ahead and jump into the computer and take a look at some real data. Again, I'm using Model Studio running on SAS Viya. In this application, we're going to pretend that we work for a chain of grocery stores that's interested in predicting whether or not customers purchase an organics product. So we've got a single target variable. It's binary, target by, and then we've got historic information on our customers, demographic information, information about prior purchases, etc. I've already done a little bit of work here. In Model Studio, the analysis is done in pipelines. I've got a single pipeline constructed. There's a neural network that is built. Notice that we've done some data pre-processing before we built the neural network. So we're in the hypothetical scenario where I've maybe built that model. Maybe I've even shown the neural network to my boss. The boss says it looks good, but can we do any better? Why do you try to build a model using a different algorithm? No problem, boss. I can get that done. How about we try a gradient boosting model? Adding models in pipelines in Model Studio is very easy. I'll start at the Data tab, right-click, Add Child Node. It's a supervised learning node, and we'll go to Gradient Boosting. Gradient boosting models do not require the same amount of data preparation that neural networks do. That's why I'm building that model straight away without any imputation, without any variable selection. Before we run things, let me take a look at some of the results that I have under data exploration. Remember, to go from cumulative response rate to cumulative lift, I need to divide by the prior event rate. Let me get that from the data exploration node. It's already been run. I'll go straight to the results, and I want to look at the summary of class variable distributions. Here it is on the right-hand side. I'll change the focus of the chart to be the target variable target by, and we see that the event rate is just under 25%. Again, remember, that's the constant value that's our denominator when we go from cumulative response to cumulative lift. All right, let's close those results. And let me go ahead and run the entire pipeline. That'll run the model comparison node. It'll obviously run the gradient boosting node along the way. And we'll start by taking a look at the results of gradient boosting when the results are ready. Okay, we've got our green check marks. The pipeline has been run. Before we do model comparison, let's go back to the gradient boosting model. Let's take a look at results. The graphical tools to assess the model performance are found under the Assessment tab. So I'll click Assessment, and the lift reports are in the upper left-hand corner, but I'll go ahead and maximize these charts. Cumulative lift is displayed by default. Let's start with the cumulative response rate. What I was calling response rate, Model Studio calls response percentage, same exact concept. So if we start with the cumulative response rate, we'll take a look. Why do we have two lines here if I'm just assessing a single model? Because we've got the performance of that model on our training and validation data sets. By the way, the right-hand side of the plot, we see that Model Studio is using some natural language processing to interpret the plot for us. We don't need that here. I'll go ahead and do the interpretation for us. Remember, this is the cumulative response rate for different depths or deciles. So maybe we're interested in the response rate in the top 20% of our customers. So I go to a depth of 20 or a decile of 0.2. I see the cumulative response rate is 65.39. Now remember, cumulative lift takes that value and divides it by the prior event rate. That's the value we saw earlier under the data exploration node, the value that was just under 25%. If I take the 65.39 divided by that prior event rate, I will get the value on the cumulative lift. Notice when I change to that plot, the lines do not change. They stayed exactly as they were, only the vertical axis changed. Validation data, cumulative lift, 2.64. Now again, that directly interprets how much better my gradient boosting model is doing at capturing events compared to a random model based on that historic event rate. At a depth of 20%, my model is capturing 2.6 more responders compared to just that naive model. So my gradient boosting model, compared to just randomly guessing for who's going to respond, is doing much better. Now, before we go to model comparison, let me show you another way that we can get to cumulative lift. It's based on a different statistic. Model Studio also gives us information on the cumulative captured response percentage. Now this isn't really a rate like we were calculating together. The cumulative captured response percentage just says at each decile or depth how many responders have been captured. So notice that if we're at a depth of 0%, we haven't captured anybody. That means we've captured 0 responders. By the time we're at a depth of 100%, we've captured everybody, so we've captured 100% of the responders. If we're focusing on that 20% decile again, we see the cumulative captured response percentage there is 52.845. Now to go from this value to cumulative lift, I'm not dividing by that constant like I showed you before. I'm dividing by whatever the decile the value comes from, or in other words, whatever depth I'm at. So in this case, to go from cumulative captured response percentage to cumulative lift, I take the 52.845, I divide it by the depth value of 20, 52.845 divided by 20 is the same value we saw for cumulative lift earlier. So there's multiple ways that we can think of calculating cumulative lift. All right, I've got 2 models on the workbench. I need to decide which one goes into production. Let's take a look at the model comparison results. We'll close that chart, close the results, right back to our pipeline. It's already been run. Let's look at the results of model comparison. The first thing we're going to see is a table that provides numeric values of model performance based on some numeric metric. The gradient boosting model is picked as the champion from the pipeline. That's okay. I want to assess things graphically using lift. So we'll go to the Assessment tab. The lift report is again in the upper left-hand corner. I'll maximize, and we'll just talk about cumulative lift. With only 2 models being compared, why are there 4 lines on this chart? Well, because we're seeing model performance on all partitions of the data. How about we focus on just one partition? We'll focus on the validation performance. 2 lines because I'm comparing the performance of 2 models. The blue line is the gradient boosting model. The yellow line is the neural network model. Sometimes the performance or these lines might bounce back and forth, where at certain deciles one model's on top, at other deciles the other model's on top. What we see here is that across all deciles, the gradient boosting model is uniformly superior. No matter where I look on this chart, the blue line is always above the yellow line. That means based on cumulative lift, the gradient boosting model is always outperforming the neural network. If I look at a depth of 20%, remember the gradient boosting model had a cumulative lift of 2.6. That means I'm getting 2.6 more responders compared to the naive model, whereas the neural network has a cumulative lift of only 2.5. I'm getting 2.5 times more responders from the neural network compared to the naive model. Clearly, comparing the 2 models, I'd want to use the gradient boosting model moving forward into production. I hope you learned some things. I hope you had fun along the way. If you've got some questions or want to leave a comment, feel free to leave it below. Don't forget to subscribe to our channel if you're not subscribed already. I'll see you later.